Hi dear children, welcome back to online class. And in the previous session, so we discussed about the magnetic dipole moment, right? So that was represented by the M, magnetic dipole moment M, that is given by the either of the pole strength of the pole and the distance between the two poles, right? And this is a formula for the magnetic dipole moment. And see dear children, this is a vector quantity and it acts in a direction from south pole to the north pole. Keep it in your mind, electric dipole also, that act or that is in the direction from the negative to positive. Similarly, means in the same way, here also the magnetic dipole moment act from the south pole to the north pole. And as you know, the SI unit of the magnetic dipole moment is what? That is ampere meter square, or another one is there, joule per Tesla, joule per Tesla, that also, or else you can write like this, joule per Tesla. Okay. Then see here, what is this? So this is the dipole, that is magnetic pole strength. Remember, QM means it is a magnetic pole strength. What is the SI unit of the magnetic pole strength? SI unit of the magnetic pole strength is ampere meter. Remember children, it is ampere meter. Yes. Then today firstly I want to draw the magnetic field lines. Draw magnetic field lines, around first one, bar magnet. How it will be? Already I think in the previous video I have shown this, no problem, we can see one more time. This is a bar magnet, take it is a north and south pole. The same you can keep like a vertical direction also, no problem, right? And that R originating from the north, terminating at the south, again they are continuous inside the magnet also. See dear children, the direction of the magnetic field is very, very important. This I shown you already, okay? And this is the representation of the magnetic field lines around a given bar magnet. This arrow mark plays very important role. Then what about second one? Around a solenoid. Around a solenoid. Solenoid means, as we know, this is a electromagnet wounded by the copper wires, like this. Copper wires are wounded around the magnet, and here will be like this structure. Okay. So then if I take this is the north pole and this is the south pole, same thing here also, the magnetic field lines you can represent this direction. Why I am stressing this, why I am explaining this means, once for the 2 marks the question came, represent or draw the magnetic field lines around a solenoid. Yes, it may be for the 2 marks. So solenoid means like this. So but remember, both bar magnet and solenoid behave same only, right? Only thing is copper wire is wounded on that core, right? So this is what the magnetic field lines. And see dear children, these magnetic field lines only can explain about the strength of the magnetic field and how much effect it is, right? Then moving to the next point, the torque. Torque acting on a magnetic needle in a uniform magnetic field. Uniform magnetic field. Actually, only you have the expression of this, but little bit we know today in the session about how that expression came, right. So, remember in the NCERT only the expression they have given, but I want to explain you how that expression came. Then before going to get that, we should have a diagram and see in the case of the physics, the diagrammatic representation plays very important. Along with that, you should have the imagination power also. Whatever concept, whatever we are dealing, when you have that imagination, you can get the idea very easily. And here I am using a magnetic needle. Yes, take this is a magnetic needle. This is a south pole and this is a north pole. That magnetic needle made an angle theta with the uniform magnetic field. And I take the length of the magnetic needle is 2L. Then what are the consideration? Consider a uniform magnetic field B and a magnetic needle of length 2L with a pole strength M kept in the B, which makes an angle theta over. Then in a first PUC you learnt that what is the torque. Then tell me what is the torque? Torque means it is the represented by a letter tau, Greek letter tau, that is equal to force into the perpendicular distance between the two lines of action of the forces. See here, dear children, when a magnetic needle is kept in the uniform magnetic field, remember it experiences the torque, no net force. Yes, so that is why here two lines of actions will be there. That torque, one force will be acting in this direction, another will be in this direction, that makes the needle to rotate around the magnetic in a magnetic field. Okay. Then if I take force into perpendicular distance, then what is the force experienced here? Force experienced F is given by, that is pole strength into the magnetic field. Pole strength into the magnetic field. Then if I take from here to here, it is the perpendicular distance, call it is A. I take it as A. Then or else here itself you can take, this is A, right, this is a theta angle here, right. Then that NA is taken as the perpendicular distance. Now what I need to find, what is that perpendicular distance? How to calculate? From the figure that is sin theta, I will take here sin theta. See, here is the theta, then sin theta means what? It is opposite side upon the hypotenuse. So better you take from here to here only. Okay. So this only we can use. Theta means it is NA upon SN. NA upon NS or SN, whichever you want. Then from this you can take NA is equal to NS into sin theta. Then NS is equal to what? It is equal to 2L sin theta. Then substitute this 2L sin theta in the first equation, that is the torque, right. Then torque tau is equal to force, we know that it is Qm into B, right, and NA means it is equal to 2L sin theta. Then just now we had a discussion about the magnetic dipole moment. The pole strength and this 2L is given by the magnetic dipole moment small m, and it is a magnetic field B into sin theta. Remember dear children, this is the torque acting on a magnetic needle. You can take magnetic needle or a bar magnet kept in a uniform magnetic field. This is the magnitude form of the torque, and torque is a vector quantity. Then how to write the same torque in the vector form? That is given as the vector form of torque is tau is equal to m cross b. Remember, here there should be the vector notation. Am I clear? Yes, I hope you understood the expression. See what I told, only you have this much only in your NCERT, but how that came you should follow this one, right? Yes. And now dear children, moving to the one more very important expression, that is time period of the magnetic needle kept in the uniform magnetic field. The question asked 2018. This question is asked in 2018. Write the expression for the time period of the magnetic needle or a bar magnet kept in the uniform magnetic field. Then how to derive that? Yes, same diagram we can use here. Yes, so I want to write here. This is a important expression and it helps you in your competitive exams also, right? That is the time period of magnetic needle or a bar magnet, both are same, means for a taking both are having the magnetic dipole moment. Magnetic needle kept in a uniform magnetic field. Then same thing, same diagram I use here. Consider uniform magnetic field. B, right? And a needle kept in a magnetic field which is having a length of 2L makes an angle theta with the direction of the magnetic field, right? Then what are the things we have to consider? Same thing, consider a uniform magnetic field and a magnetic needle of a pole strength m and the distance 2L, which makes a small angle theta with the direction of the magnetic field, that is B, right? Then we got the formula of the torque acting on the magnetic needle, that is tau is equal to mb sin theta. Am I clear? Yes. Then in the rotational motion of the first PU chapter, we learnt about the torque. There we used one more formula, that is torque is equal to I into alpha. Can you remember this, children? Yes, that is tau is equal to I alpha. Then what is the I here? Moment of inertia of the magnetic needle. And what is alpha here? Alpha is the angular acceleration. Then by seeing these two formula, what you feel? The LHS is same only. That is why when you compare both the equation, we get that the torque, that is one is a mb sin theta and the another one is I alpha. Therefore, I alpha is equal to mb sin theta by comparing both the equation. Then again we know that we have what alpha means, it is the rate of change of angular velocity with respect to the time, right. Then again we have keep the d by dt as it is. Omega means what? It is the angular velocity. How to obtain that? It is the rate of change of angular displacement with respect to the time. Then that is given as d theta upon dt. Here theta means what? Angular displacement. Am I clear? Yes. Then when you take alpha is equal to, when you simplify this, you will get d square theta upon dt square, right. Substitute in this in the above equation, then I d square theta upon dt square is equal to, what is my expression? mb sin theta. And here if theta is small, you can use sin theta approximates to theta only. So in the place of sin theta, we can replace that by theta only. So I into d square theta upon dt square is equal to mb theta. Then this I take here, d square theta upon dt square is equal to mb upon I into theta. Call it is equation number 1. Equation number 1. Then by seeing this, children, again can you remember one more formula in the case of wave motion? That is simple harmonic motion. See the equation 1 we can compare with the simple harmonic motion equation. What is that equation? That is alpha is equal to minus omega square x, right. X means here this is the displacement, that is theta we can take. Then when you compare again here, alpha is nothing but d square theta upon dt square, okay. So you can use like this, d square theta upon dt square is equal to omega square into theta, call equation number 2. So compare both the equation 1 and 2. Compare 1 and 2, we get what we get here, that is minus omega square is equal to mb upon I. mb because theta common, so only the term is omega square is equal to, and neglect this negative sign. Yes, that shows it is opposite to the given magnetic field. Negative sign what? The angular, so velocity is opposite to the magnetic field. Then by this again we can simplify, omega is equal to root of mb upon I. mb upon I. Am I clear? Yes, we are at the last step, that is the time period of the magnetic needle. Then we have the time period t is equal to, what is the formula? T is equal to 2 pi upon omega. This also you know in the simple harmonic motion, right. Then t is equal to 2 pi, in the place of omega what I can substitute now? That is root of mb upon I. Then again simplify this, you get that 2 pi root of I upon mb. This is the very important expression for the time period of the that magnetic needle. Clear? Yes, and see here question will come, write the expression of the time period of the magnetic field in the uniform magnetic field. then you have to write T is equal, the question comes, write the expression for the time period of the magnetic needle in a uniform magnetic field. Then what is that formula? T is equal to 2 pi root of I upon MB, and compulsorily you should mention what is the IMB. What is the T time period? What is the I? Moment of inertia of the needle. What is the M? That is magnetic dipole moment. What is the B? That is the magnetic uniform magnetic field strength. Am I clear? Yes. And with this, one more last expression is the frequency. We can also obtain, if we know the formula of the time period, we can also get the frequency, because we know that the frequency is reciprocal of the time period. So, the frequency can be given as frequency of magnetic needle is given as nu is equal to 1 upon T. Then that is equal to, T means already we have formula here, that is 1 upon 2 pi root of I upon MB. Then again simplifying, this means frequency nu is equal to 1 upon 2 pi root of MB upon I. This is our expression, and where you write nu is a frequency, and M is the magnetic dipole moment, and B is the magnetic field strength, and I is moment of inertia, of magnetic needle. Yes, I hope, dear children, today whatever the points we have discussed, so that the points I explained you understood, very nice. If any doubts, you can ask me. Yes, it is clear, and remember, so today we talked about the magnetic dipole moment and its further, so what expression and the SI unit. Then we move to the important part, that is drawing the magnetic field lines around the bar magnet and also around the solenoid, right. And then so we talked about the torque acting on the magnetic needle, which is kept in the uniform magnetic field, right. That is tau is equal to MB sin theta, it is a magnitude form, and tau is equal to vector M cross B, that is the vector form of the torque, right. Torque, the SI unit already you know, that is Newton meter. Clear? And moving to the very important expression, that is the time period of the magnetic needle in the uniform magnetic field, that is T is equal to 2 pi, that is root of I upon MB. Yes, and if you know the time period, definitely you can get the frequency of that magnetic needle in the magnetic field, that is nu is equal to 1 upon 2 pi root of MB by I. Yes, thank you, dear children, for watching the video, and if any queries you can ask me. Okay, so take care, thank you.